In Topic 2, we'll be focusing on quadratic functions. For Lesson 1 specifically, our topic essential question is, how do you use quadratic functions to model situations and solve problems? If you flash back to Section 1-2 in the last topic, we talked about vertical and horizontal shifts. That is, when you had a parent function. For this function, we were working with the absolute value of x. So when we put this plus 3 outside, whether it was in the function or the original equation notation, that moved it up 3. Or the minus 7 on the outside moved it down 7. These were your vertical shifts. Your horizontal shifts were located inside the parentheses for function notation, or within the actual equation there, inside the brackets. Remember, it was always the opposite of what we thought. So minus 4 would actually move to the right 4, and plus 2 would move back 2. We'll be using these ideas in this same section, which I think will make it seem pretty easy as we begin. You'll often be asked about key features of the graph. So over here, I have a blue parabola graphed. Now you will see this blue equation down here is what I've typed. We call this standard form. It looks like a general parabola like you've seen graphed before. Notice how it says I have another purple graph graphed here, but you don't see it. That's because it's hidden right underneath. So I've actually graphed the same equation twice, but I've used a different form. We call this form vertex form, and we'll get to more on that here a little bit later. But again, remember, I do have two parabolas graphed. They just are in a different form. So it's technically not two, it's actually one with two different equation types. So over here, key features might include our x-intercepts, our y-intercept, and this very bottom point down here we refer to as the vertex. It's either the top point of a parabola or the bottom point. One other piece that we might discuss in this chapter is referred to as the line of symmetry. Think of folding this parabola. Where would it fold nicely? This right here, it goes through the vertex every time. This is called our line of symmetry. Our goal in this section is to find all these key points very quickly without having to graph them. And both these vertex and standard equations are going to be very helpful in doing that. With Topic 2, you'll find we'll be dealing with quadratic equations or parabolas the entire time. Their essential question for the entire topic is, how do you use quadratic functions to model situations and solve problems? If we look more specifically into 2.1, we'll notice it starts out by flashing back to what we did in section 1-2. We talked about vertical shifts. That's when the function would move up and down. So if our parent function was the absolute value of x, this plus 3 on the outside moved it up 3, or this minus 7 on the outside moved it down 7. Those were our vertical shifts. Our horizontal shifts were the ones that were tucked inside either the function itself or that function notation. Recall that if it's inside those parentheses or the function itself, it moves at the opposite direction of what you might think. So when you see a minus 4, it will horizontally shift it to the right 4, or when you see a plus 2, it shifts it back or to the left 2. Keep these ideas in mind as we begin Section 2.1, and I think you'll find them quite helpful. Section 2.1 begins by identifying key features. Now, if we look at this graph, you might point out some interesting points. I've also graphed them with Desmos. Here we have a couple x-intercepts, and we also have our y-intercept. And down here, you may know this point is referred to as the vertex. Now, a vertex can be at the top of a parabola, should it open downward, but that's the very top or the very bottom of the parabola. There also is a special line that cuts right down the middle of the parabola as if you were going to fold it in half. This line always goes through the vertex, and it is called the line of symmetry. You'll be finding all these key features of the graph with special equations, and you won't even have to graph them by the time we're done. But one thing I want to point out is it looks like I've only graphed one function over here. You see this blue color and you see my blue graph. That's what I've graphed there. We call this form of the equation the standard form. It's what we're used to seeing, something x squared and something x and a number by itself. There also is a second function. You can see the purple is turned on here, but you don't see the graph. It's actually because it's underneath there. So I've technically graphed the same parabola 2 times, but we call this form the vertex form. We're going to find it important to use the vertex form and the standard form of the parabola to find these key features. But again, note I've only graphed one parabola. I just have 2 various forms of the parabola at this time. The essential question in 2-1 is how does the equation of a quadratic function, remember that's just a parabola, in vertex form highlight key features of the function's graph? So again, we're looking for these key features, but the vertex form that I introduced you to on the last slide has some special qualities that help us find these key features quicker. So with quadratic functions, again, we've normally been seeing a function like this, and we think of that as our standard form. It's usually the one you learn first. But also, and it's important to note, our parent function is going to be the x squared graph here. Okay, so we're just going to refer to that as our basic quadratic parent function. But the vertex form looks something like this, and you'll want to take note of this. We'll practice it a lot. There are lots of different variables in there, and we're going to figure out what each of those variables will do for our quadratic equation. Let's start with something we might know from the last chapter. We talked about if something was inside, if there was a number added or subtracted inside this parenthesis, especially when dealing with absolute value. But it works the same for a quadratic or an x squared graph. This h value is your horizontal translation. It will tell you how the parent graph x squared moved left or right. Whereas our k value over here, the k value will give us our vertical translation. And that means it will tell us how much up or down the original parent graph x squared moved. This a value, you've probably dealt with it before. Most kids know that if the a is positive, it will open upwards, and if the a is negative, so if it's a positive a, it means it opens upwards, and that's still going to be true. If there's a negative a value, it's going to open downwards. So the a value can tell us which direction the graph is opening. It can also tell us whether it is a vertical stretch or compression. So to get even more specific, if our a value is large, say greater than 1, if the a value is greater than 1, it's a vertical stretch. If your a value is between 0 and 1, then it's a compression. So that basically means if that a value out front is a fraction, it will vertically compress, kind of smoosh down your graph. And we learned that in section 1 too, but we might want to focus more on what this actually finds for us when it comes to key features. Now I've added a little bit here for this part A on example 1. This first graph that they've given us is the parent function. We know it's the basic x squared because it starts at 0, 0. It looks like a parabola opening up. And the main key feature of a basic parabola, or the parent function, is it always has a 1, 1 coordinate. It goes over 1, up 1, and back 1, up 1. You'll want to watch that to check if it's ever had a vertical or horizontal compression, or stretch. But now we want to see what this equation would do to it. So we have a negative out front. That means it will eventually open down. Remember that reflection over the x-axis. The 1/2, that's a fraction, so we know it's going to be a vertical compression. It's going to go half as high when it steps over 1 as it did before. This 2, remember when it's a +2 in the parenthesis, it always goes the opposite direction we're thinking, so it's going to go back 2. It is not going to vertically shift though because it has no number. Now I wrote a +0, and I'll show you why. So what this is going to do is take my original parent function and move it to the left 2, but not up at all. So this will be my new vertex. Now, it is going to flip it over the x-axis. So instead of going up, it will come down. It's not going to go over 1, down 1, though. It's going to go over 1, down 1/2. It's going to compress. It's going to be wider, if you will, or flatter. This would be more of my parabola when I am done graphing. Now, what we want to note about the vertex of it, and I wrote the numbers here color coordinated, since that moved it to the left too, but not up or down, that moved my vertex. There is my new vertex for my transformed function. So looking at example 1 part B, I've now indicated that the 2 means of vertical stretch times 2 kind of messes with that slope, if you will, for the first point. And this -1 will move it to the right 1, and the -3 will move it down 3. Let's take a look at the graph. So if I went to the right 1 and down 3 to make my vertex, it's still going to open up because it's positive. But my vertical stretch says now instead of going over 1, up 1, it's going to over 1 and go up twice as tall. So this would be the beginnings of my new function, my transform function. Check out this vertex though. Your vertex is now 1, -3. You can start to use these numbers to get your vertex very quickly. You won't even have to plot it because you know how it moves from 0, 0. So using vertex form gives you just that, your vertex, very quickly. That's why, if we go back to this little notes page here, when you're given a vertex form with your x minus h quantity squared plus k, your vertex is always this h value. Kind of notice how we ignore that negative. So if it's a negative h, it'll be a positive h here. If it would be a plus h or a plus 7, it'd be the negative of that here. And then your k value just drops in. That is your new vertex. I won't graph these ones, but notice how this is going to flip it over the x-axis, upside down or open downwards, if you will. This will shift it to the left 2 and doesn't shift it anywhere. It's a 0 here. So my new vertex will be -2, 0. You could graph that on Desmos to check it, or use your transformations to help you graph that. But again, over here, your vertex on this one is going to be 1, 2. You'll see how quickly you can make your vertex when you use vertex form. So for example 2, when someone asks you the key features of this graph, they've graphed it for you so it helps to see, but I can use these numbers right here and know my vertex is +3 because it moves it in the opposite direction, and up 4. I also know that down the center of this line is my line of symmetry. Okay, that means x is always going to be 3 there, so that'd be my line of symmetry. We may take it back to asking about domain and range. So for example, this parabola, it would go on forever. We don't have the arrows, but we could. The domain would go from -infinity to infinity. And our range, remember how high or how low it goes, would start at 4. It's the highest or the lowest y value it has, all the way up to infinity. One thing to note, they may ask if it has a minimum or a maximum. Because it opens upward and it goes up forever, we also refer to this vertex as a minimum value. On example 2, the triads, the same idea. Now you can always graph this on Desmos and take a look at it, but you should be able to tell the vertex really fast from it. You should be able to tell that it opens down, so you would have a maximum. And you'll find other pieces, like the line of symmetry. Remember, that's what cuts your parabola in half, and it would cut your parabola at an x value where it crosses through that little tallest point or lowest point called the vertex. So this tells you your line of symmetry is at x equals -4. Again, domain and range, because it's a parabola, your domain would be all real numbers. And your range, it used to go from 0 up, remember the original one? But now it got flipped upside down and went to -5. So it's going to go from, your range would go from negative infinity, we should say, to -5. But graph that to double check it. In this first video, we focused a lot on going from equations and finding key points of the graph with getting the equation first. In the next sections, you'll be taking the graph with the key points and making the equations. So we have traveled this way. Watch the next video to be able to travel this way.